Hey everybody, Dr. Retzik here with you. This is our last video of the quarter. Congratulations. Let's get started. So we've established Green's theorem, which is some connection between double integrals and line integrals. And what we've done so far is we've said, oh, okay, well, if you have to do this line integral, you could turn it into a chapter 15 problem and instead do a double integral over the enclosed region. And often those double integrals are just a little more straightforward. You don't have to parametrize anything. May not have to break the piecewise smooth boundary curve into a bunch of pieces and parametrize each piece and deal with all that. You could just do a straight up chapter 15 double integral, and that's great. Okay, today's discussion is about some kind of an inverse idea to that idea. So check this out. This is another example of kind of a deep mathematical curiosity. So there's a closed curve. Let's say it's being traced out counterclockwise, positive orientation if you like, and the region inside has some area and we'd like to find it. Now as I'm shading this in, I want you to imagine trying to find this area by way of chapter 15 techniques. Right, you would do a double integral over the entire region of the constant function 1. But man, the setup for that double integral over this region, it just seems kind of outrageously hard. I mean, what is this? Right curve minus left curve, top curve minus bottom curve. You have to break it into a bunch of subregions. I don't know, it just looks really hard. It's not polar, it's not screaming out for polar. I don't know, finding the area of that region, that kind of blob, just looks not that easy. And yet you want to find its area. So we're looking for the area of the region R. And we know in a chapter 15 way, well, I mean, in principle, it's the double integral over R of 1 dA. But we really don't want to do that double integral. That looks terrible. Okay. An exceedingly clever use of Green's theorem is to say, well, okay, fine, you don't want to do the double integral? Let's Green's theorem this thing. Equals, by Green's theorem, the positively oriented line integral of, let's say, m dx plus n dy. And you look at that and you say, wait, where'd you get that equal sign? No, hang on. This thing, what are you even talking about, Retzik? This is this by Green's theorem. Okay, so this is a dot product with dx dy, so that's the one that goes along the curve. And so along the curve, that was the dn dx. Take away dm dy. All done dA. That's Green's theorem, right? It's not, this line integral doesn't equal 1 in the double integral. It's dn dx minus dm dy. Surely. Why should it equal 1? Well, here's the thing. At the start of this problem, this was a chapter 15 problem, and no one mentioned a vector field. So you could bring a vector field to the table where it just so happens that dn dx minus dm dy comes out to 1. So this equals sign here, this is totally legit. Provided dn dx minus dm dy comes out to 1. That would be true by Green's theorem. Can you think of a vector field, anything you like, it's your choice. Can you think of a vector field such that dn dx, take away dm dy, comes out to 1? Let's try and think of one. How about, all right, so we want the second one dx minus the first one dy to be 1. I got one. Ha! Ha! We did it! Right? dn dx minus dm dy is 1. I mean, it's sort of a cheesy example, but we're the ones bringing the vector field to the problem right now. Now, that's not the only one, of course. I mean, you could have said, how about, could have gone this route. How about negative y comma 0? That'll do it. dn dx, take away dm dy, that's 1. I mean, and the list is infinite, in fact. I mean, you could have done this if you felt like it. Again, dn dx minus dm dy comes out to 1. This goes on and on and on. You have infinitely many different vector fields you could opt to introduce to this seemingly chapter 15 problem in order to make progress. Now let's imagine what this looks like depending on our choice. Okay, so let's say we chose this one. If you choose that one, then what's this line integral come out to? It comes out to positively oriented line integral around the curve C, m, which is 0, times dx, plus n, which is x, times dy. Yeah, there we go. Boom. If you want the area of a region R enclosed by a simple piecewise smooth closed curve C, then to figure out that area, all you have to do is the line integral x dy around the boundary. Or say you had chosen this one. What if you went with that one instead? Or, well, what would that one be telling us? That one would be telling us that that line integral is integral around C negative y dx. So negative integral around C y dx. Maybe you prefer that one. That one also tells you the area of the enclosed region. Or what if you had gone with this one? That one would have resulted in this statement. All right, what is m dx plus n dy? Let's see, let's bring that half out in front. Integral around C. Okay, m dx. Well, m is the negative 1, and n is the positive 1. Can we write it like this? X dy minus y dx. And that also tells you the area of the enclosed region. any of those integrals comes out the same by Green's theorem and comes out to the area of the enclosed region. So now you have this totally separate chapter 15 becomes chapter 16 method for computing the area of an enclosed region. And I find it remarkable, it's mathematically amazing to me that the curve, C, in effect knows how much area it is enclosing. Because we've just argued that the area of the enclosed region hinges on an integral only around the boundary. So here's a concrete example where the boundary tells the full story. The total enclosed area is computed solely from data from the boundary. And it kind of makes sense, right? Like when you throw a rubber band down on the table and you get this weird kind of blob that it encloses. Still, the blob it encloses is sort of intrinsically connected to the shape that the rubber band is in. So somehow the shape of that enclosing curve is telling us what is the area of the enclosed region. There's a beautiful mathematical theorem called the isoperimetric inequality, which has to do with this very idea. Of all curves of equal perimeter, which one do you think encloses the most area? All curves equal perimeter, so you have a certain amount of fencing for a pasture. Of all the possible enclosures, which one will have the most area? It's a beautiful question. It has some geometric intuition behind it. I'll leave it to you to think about what shape enclosure you would use for a given amount of fencing. Anyhow, deep connection between area and the bounding curve given to us by Green's theorem. Okay, that's it. 16.4 done. Chapter 16 done. Calc 4 done. Come to class with questions. Let's wrap it all up, and then let's just prep for the final later this week. All right. See ya.